show the character of the final closing tracings as the teeth reach their intercuspal position. The incisor point can be seen thrusting forward during opening. This could be expected knowing that both condyles translate forward immediately and simultaneously during opening phase of chewing. The incisor point closing strokes follow posterior to the opening strokes. This is explained by the early return of the working condyle to its posterior and lateral position. The working condyle affects the movement of the entire mandible. This produces lateral gliding contacts between opposing canines and no closing gliding contacts between the incisor teeth. Terminal hinge closure is not seen because the jaw does not close with both condyles in their terminal hinge positions. The superior view of the mandible also shows the variations in timing between the working and non-working side. Here, the food is on the right side. We now focus our attention to the right working side condyle. Shown next are three typical working side chews. Opening is nearly straightforward, while closing shows a lateral and posterior movement. Here the food is placed on the left side. We are watching the action of the non-working condyle. After a forward opening movement, the condyle moves medially influenced by chewing on the left side. Let's now analyze the movements related to articulator controls. The yellow arrow superimposed over the non-working side closing stroke corresponds to the Bennett angle setting of the articulators. The non-working side condyle makes a smooth closing movement directly to its intercuspal position at point 1. The working side condyle, however, makes a final closure movement from 7 to 8 to 1, represented by Bennett movement or side shift adjustments of articulators. Here we see an example of an articulator adjusted to allow for an extreme amount of working side Bennett movement. For most people, this movement measures less than 1 millimeter. This is the subject with the severely worn teeth. He has an extreme amount of Bennett movement. The top view of the left working side condyle shows lateral closure strokes, which are followed by medial movements with no identifiable intercuspal position. When food is chewed on the right side, the left non-working side also shows the extreme looseness of the joint. We are now looking up at the right working side condylar sphere of the articulator mounted in the replicator, while our subject with severely worn teeth is chewing. Again, we see the effect of the looseness of the joint, which also affects contacts on the occlusal surfaces of the teeth. As we watch the lower right molar chewing patterns, the horizontal sliding of the teeth through the intercuspal position is evident in this patient with worn teeth. The opening movement adds another dimension to this view. The computer plots also demonstrate the excessive horizontal movement pattern. In this demonstration, you have seen that the typical chewing pattern of an adult with good occlusion is characterized by midline opening movements, wide lateral closures, frequent gliding tooth contacts, and a pause in the intercuspal position. Condylar movements during chewing are shown to reach their borders, which are simulated by articulators. You have also seen an example of a subject with extremely worn teeth and excessive lateral movements in the joints.
Jaw movement characteristics differ from one individual to another and thus provide a very interesting subject for scientific study. This motion picture presents a new method of measuring and recording these movements by engraving them in clear resin blocks. The recording is performed with a specially designed experimental pantograph, which culminated 6 years of research effort. In order to attach the device to the patient's jaws, a set of custom-made plastic clutches are used. The recording pantograph consists of 2 face bows. One is fixed to the upper jaw, and the other is fixed to the lower jaw to move with the mandible. The upper bow is a rigid, lightweight metal structure, which holds 3 clear polyester resin recording blocks in fixed spatial relationships to each other and to the orbital axis plane of the patient's head. 2 of the recording blocks cover the region of hinge axis movements, and the third is centered in front of the face. A pointer located on the right side of the bow orients the recordings to the orbital axis plane of reference. The lower face bow is also a rigid, lightweight metal structure. It supports 3 recording drills, which are driven by high-speed air turbines. 2 of the drills are horizontally aligned on a common axis with their tips located precisely at a standardized distance of 220 millimeters apart. These 2 drills, in combination with the anterior drill, form a recording tripod. The clutches are cemented over the subject's teeth with a zinc oxide and eugenol impression paste. A U-shaped frame is attached to the maxillary clutch to hold the upper recording bow. Note the two attachment cups on the frame. A similar U-shaped frame is joined to the mandibular clutch to attach the lower recording bow. The two cups on the upper frame are filled with quick-setting plaster in preparation for attaching the upper bow to the maxilla. This is accomplished by inserting the ends of two vertical rods of the bow into the soft plaster. While the plaster is setting, the points of the two alignment pins are held to the axis spots which have been previously located and marked by conventional methods. This procedure not only centers the bow on the patient's head, but also orients it so that the axis of the two alignment pins is collinear with the hinge axis of the mandible in centric relation. The two alignment pins are removed from the alignment blocks, and the subject is placed in a supine position. The mandibular bow is lowered over the attachment frame so that the ends of the frame protrude freely through the attachment tubes. The lateral recording drills, which have a common axis, are inserted into the holes previously occupied by the alignment pins of the upper bow. Plaster is placed in the tubes to attach the bow solidly to the mandible. The mandible is retruded several times and finally held in centric relation while the plaster sets. The hinge axis of the mandible has now been made collinear to the axis of the recording drills. The drills are retracted from the alignment blocks, thus leaving the lower bow supported totally by the mandible. The mandible is retruded and the drills reinserted to check the accuracy of the axis mounting. The drills are again retracted so that the alignment blocks may be removed and replaced with recording blanks. A clear plastic shield is placed over the patient's face to protect him from the resin particles generated by the drills. The subject is rehearsed in the various movements to be recorded. With the mandible in centric relation, the anterior drill is activated and inserted into its recording block. It is locked at a depth indicated by a scale on the side of the turbine carriage. The left lateral border movement is recorded with the drill engraving a three-dimensional pathway. The mandible is retruded to centric relation and the drill reinserted into the recording block the same depth as before. The right lateral recording is accomplished by having the subject move his mandible slowly to the right while the drill cuts the pathway. The mandible is returned to centric relation and the recording of the protrusive movement is made in a similar manner. The left lateral recording is verified by repeating the border movement to the left. And then to the right. These repeat movements are done to make sure that the mandible was tracing a true border movement. The protrusive recording is verified by repeating the movement. The mandible is again placed in centric relation in preparation for recording the movements of the hinge axis. With the mandible in centric relation, the two-axis drills are made to penetrate their associated recording blocks a predetermined depth, as indicated by calibrations on the turbine carriage. The turbine carriages are locked when the drill tips are precisely at the standardized distance of 220 millimeters apart. The left lateral movement is shown being recorded on the right side of the patient. While the right side drill is recording the left lateral movement as shown here, the left side drill, which cannot be seen, is recording the same movement in a reverse direction. The mandible is returned to centric relation with the drills inactive. The right lateral movement is now recorded and appears on the working side as a backlash. The mandible is returned to centric relation with the drills inactive. The axis record blocks are switched from right to left so that the blank sides may be used for recording the protrusive movement. The mandible is retruded to centric relation and the axis recording drills are made to penetrate the new sides of the record blocks. They are locked at the same depth as they were for the recording of the lateral jaw movements. The same 2 points 220 millimeters apart on the hinge axis which were previously traced in the lateral jaw movements are traced in the protrusive movement. The mandible is returned to centric relation with the recording drills inactivated. The anterior reference pointer is adjusted and secured to the orbital spot on the right side of the nose. Note that the orbital spot has been marked temporarily with dark ink for photographic clarity. The recording equipment is removed from the patient by loosening the attachment clamps. Here in these resin blocks are recorded in 3 dimensions the right and left lateral and protrusive movements of this patient's mandible. Part 2 of this motion picture will show how the information stored in these 3 blocks is reconverted by a secondary pantograph to locations near the condyles. This procedure produces a pair of motion analogs which will serve to guide and control the movements of an articulator for simulating this patient's characteristic jaw movements. Shown here is a full view of the reconverter, which is a second pantograph used to generate analog guides for an articulator. The T-shaped upper frame is removed and compared to the maxillary counterpart of the patient recording pantograph. The mandibular bow of the patient recorder is compared to the counterpart of the reconverter to show the smooth steel guide pins which substitute for the recording drills. The frames of the reconverter are locked together in centric relation by utilizing the centric position of the protrusive recordings. The guide pins are retracted from the recordings and the upper frame is lifted on its pivoting post so that the analog blocks can be secured in position. Both the clear recording and the blue analog blocks are made of polyester resin so that the heat generated by the drills will not melt or distort them during the pantographing procedures. The analog blocks are lowered slowly over the hemispherical-ended analog mills to form centric openings. The frame is guided precisely downward to centric by a series of 4 vertical posts, one of which can be seen to the right of the blue block. After the centric openings have been generated, the guide pins are reinserted and locked into the centric portion of the protrusive recordings. The 4 vertical posts, which ensure the precise centric openings in the blocks, are raised and locked out of position so that the patient's recordings can guide the movements of the T-frame for generating the analogs. The 1/4-inch vertical mills are activated with a foot control, and the frame is moved distally while being guided by the protrusive recordings. Shown here is a close view of the protrusive movement being pantographed on the axis near the condyle level. The actual intercondylar distance of the patient is of no significance with this system. However, the location of these vertical analog mills is at the average anatomical intercondylar distance of 110 millimeters, which makes a convenient size articulator for practical laboratory work. In this view, we see the entire upper frame being guided by the 3 recording blocks. This close view shows the anterior block guiding the frame in the protrusive motion. We now inspect the completed protrusive movement analogs. The pointer is indicating that the patient's recording blocks have now been reversed to expose the lateral border recordings to the guide pins. The analogs are repositioned over the vertical mills in centric relation, and the guide pins are inserted into the lateral border recordings. Here we see the right recording with an analog being generated on the left. Note the backlash effect in the recording was caused by the pivotal action of the working condyle. Observe that the Bennett and orbiting paths are magnifications of the movements at the condyle level. A closer view of the recording shows the backlash effect. On the left, starting in centric, we see the lateral and medial Bennett shift of the working condyle, followed by the curvilinear Bennett and orbiting movements. A closer view of the guide pin shows the lateral Bennett shift and backlash, the medial Bennett shift, and the Bennett and orbiting paths. This view shows the anterior recording of the lateral border movements. Note the twisting motion of the frame as it rotates and translates in the 3 planes of space. After the border movements have been generated in the analogs, the guide pins are retracted and the analogs examined at close range. In the right analog, we see outlined the border movements including the Bennett, orbiting, and protrusive paths. Here we see the same movements on the left. This view shows that the condylar elements of the articulator and centric indicating key are spaced exactly like their counterparts on the reconverter. The analogs are removed and attached directly to the maxillary frame of the articulator for replay. Observe the right condylar element as it moves from centric to protrusion and back to centric. Outward and inward Bennett shift, inward on the Bennett, and orbiting paths. In the right working path, the balancing Bennett and orbiting paths, and back to centric. The centric pin is depressed to position the condylar elements in centric relation.